Backend is huge, and if we start discussing every single component that could be part of it, we will be stuck here for years. So what we will do is we will only discuss those topics which are used in majority of the code bases, let's say 90% of them. With that in mind, let's talk about HTTP protocol, the medium through which our browsers talk to our servers, either to send data or to receive data from it. And as I said, there are a lot of other ways and protocols which clients and servers use to communicate with each other, and HTTP being one of the most used ones. We will focus on that. Now, there are two ideas which are at the heart of HTTP protocol. The first one being statelessness. What does it mean? Statelessness basically means it has no memory of past interactions. So each HTTP request carries all the necessary information for the server to process it, such as headers or URLs and methods, which we will see in a bit. And after the server responds, it forgets about the request. If a client makes another request, the server treats it as a new and unrelated event. And it also means self-contained requests. Since the server does not remember past requests, each request must include all the necessary data, such as authentication tokens or session information to handle that specific interaction. For example, in the case of accessing a user profile, the client has to provide credentials like cookies or tokens on every request for the server to know which user is requesting the data. So what are the benefits of that? What are the benefits of this stateless model? The obvious one being simplicity. Stateless design simplifies server architecture because the server does not need to store session information, which would otherwise require additional resources and complexity. And it also means scalability. Stateless protocol makes it easy to distribute requests across multiple servers because no single server needs to keep track of a session. And if the server crashes, it does not affect the state of a client interaction, as there is no session or memory of a request that needs to be restored. And having said that, because HTTP is stateless, developers often implement state management techniques like cookies or sessions or tokens to maintain continuity in interactions where needed, like user logins or shopping carts. And we will explore those soon in this series. And the second idea is client server model. In a typical HTTP request flow, there is a client and there is a server, always. The client typically is a web browser or an application which initiates the communication by sending a request to the server. The client is responsible for providing all information needed by the server, such as the URL of the resource or the headers and everything. And then there is the server, which hosts resources like websites or APIs or other content and waits for incoming requests from the clients. When the server receives a request, it processes it and sends back the appropriate response, such as a web page or data or error message or a JSON file or a text file or any other kind of content. Now, the thing to remember here is HTTP protocol states that communication is always initiated by the client to get some kind of response by the server. And throughout our discussion, we can go ahead and safely assume that HTTP and HTTPS are interchangeable, because HTTPS, to oversimplify it, just a more secure version of HTTP, but the underlying principles are the same with more security features like encryption and security certificates or TLS, stuff like that, which borders too much into the network engineering domain. Also, to send some kind of request or receive some kind of response, first the client and the server need to establish some kind of connection mechanism, right? Otherwise, how are they going to communicate? What is the medium of the communication? And for that, HTTP uses TCP, which is a protocol, which is a transmission protocol. Essentially, HTTP does not require the underlying transport protocol to be connection based. It only requires it to be reliable and not lose messages, at minimum presenting an error in such cases. And among the two most common transport protocols on the internet, which are TCP and UDP, TCP is considered to be more reliable. HTTP therefore relies on the TCP standard, which is connection based. Now, this is called an OSI model, which is often referred when we are talking about sending and receiving data over a network, right? And we as backend engineers often deal with this layer, the top layer. the layer 7 application layer. And so a lot of discussions, for example, the recent one which we talked about, the TCP handshake and establishing connections and TLS encryptions, they often border into these layers. So they are mostly network engineering concepts. Of course, it's good to know about those, but if we start exploring those, it will be a rabbit hole and we'll have to cover a lot of concepts, right? So what we'll do is we'll focus on the application layer with a brief about what happens in the network layer. Like as I said, HTTP uses TCP and TCP uses something like a three-way handshake, which if you're curious about, you can just look up and study more on that. Now, throughout the years, we had different versions of HTTP, which kept redefining how clients and servers send and receive data, right? In HTTP 1.0, each request opened a new connection. This led to inefficiencies since a connection had to be established and closed for every request and response, which slowed performance. In HTTP 1.1, they introduced something called as persistent connections, allowing multiple requests and responses over the same connection, over the same TCP connection that was established before sending the request, which significantly improved performance. It also added stuff like chunk transfer encoding and better caching mechanisms. In HTTP 2.0, they introduced multiplexing, allowing multiple requests or responses over a single connection. It uses something called binary framing instead of text and supports header compression with HPAC and server push, allowing servers to send resources before the client requests them. Now in HTTP 3.0, built on QUIC protocol, a transport layer protocol over UDP, right? Instead of TCP, it is designed over UDP, which improved performance with faster connection establishment, reduced latency, and better handling of packet loss. It also continues to support multiplexing without head-of-line blocking, which was still an issue in HTTP 2.0. Now again, that's a rabbit hole if we get too much into the network stuff. All we need to remember is that from all these discussions, that client and servers establish some kind of network connection and messages are sent and received. That's all you need to remember for now. Now that we mentioned message, let's look at what HTTP messages look like, request messages or response messages. A request message is basically the one that is sent by the client, and a response message is the one that is received by the client from the server. So this is what a request message looks like in HTTP, and this is what a response message looks like. I intentionally took more complex messages which had more parameters, and so that we can cover different components one by one. So on a high level, I'll just explain what is what in this, right? This part, this is called a request method. This is the resource URL, the one we are requesting from the server. This is the HTTP version, which says we are using HTTP version 1.1, which is currently the most used one. This is the host, right? Which is our domain, the front end's domain. And these are all of these things, these are called headers, right? We will talk about headers soon. There will be a blank line here after all the headers to signify that the headers are over and body starts. This is called a request body, some information the client wants to send to a server, right? And in the response message, again, we have the HTTP version, we have the status code and the value of the status code, which basically means the status code 200 means okay, right? And we have again some response headers. After that, there is a blank line and we have the response body. So let's talk about HTTP headers first, right? This is very important since it's the major part of the request here and the responses. On a high level, what we can see is headers are basically key value pairs of different parameters that is sent over request or received over a response. That is the first definition. And the next question is, why do we need headers? Why not send all these values in the URL, or we have this request body here? Why create a different section just for sending more information or more metadata about the request or the response? Why create another level of abstraction? And in order to understand that, let's take a real life example. We send parcels, right? Couriers, and we receive them. The address or the phone number of the recipient and different details, right? The state, the pin code, and all of these things. Do we keep it inside the package or do we write it on top? And we write it on top. Why? Because the one who is taking the parcel from the sender and to the receiver, they need to know different informations in order to successfully transmit the package through different modes of transmission. And if we kept all those information inside the parcel, they have to open that, right? And which does not make any sense, but just for the sake of the example, they have to open that and they have to see who is the recipient again and again. So let's say another person wants to see the address, so again they have to open that. So keeping the metadata, the address and the information of the recipient on top of the parcel gives a quick way of checking different metadata about the package. HTTP headers can be thought of something like that, but they have more uses. So before we go into the use cases, let's see what are some different kinds of headers that we see. So as you can see, there are a lot of different types of headers. So can we categorize them? Can we categorize them in different types of headers? So let's see. The first category can be request headers, which are sent by the client to the server to provide some kind of information about the request itself. It could be user agent, which identifies what kind of client is that. It is a browser, or it is Postman, or it is some kind of server, or it's a mobile app. We have authorization, which sends different credentials like bearer token to the server to identify the user. We have accept headers, which provides informations like what kind of content we are expecting, whether it is a JSON, whether it is a text, whether it is an HTML file. So request headers help server understand the client's environment, its preferences, and its capabilities. Then we have general headers, which are used in both request and responses, which have some metadata about the message itself. For example, the date of the message and different caching mechanisms like no cache or max age, and the connection information, whether to keep it alive or to close it. So general headers have some kind of information about the request message or the response message. Then we have representation headers, which primarily deal with the representation of the resource being transmitted, whether it could be a request body or a response message. The content type describes the media type of the request or the response. It could be JSON or it could be HTML. The content length describes the size of the resource in bytes. The content encoding specifies any encoding like gzip or dflare. Then we have e-tag, a unique identifier, which is mostly used for caching. So representation headers provides information about the body of the message or the response, ensuring the clients and servers know how to interpret and process request or the response. Then we have security headers, which are used to enhance the security of the request and response by controlling behaviors like content loading, cookies, and encryption. HSTS ensures that the client only communicates with the server over HTTPS, preventing protocol downgrade attack. Content security policy restricts the sources from which content like JavaScript or CSS and images can be loaded, helping prevent cross-site scripting attacks. Xframe options prevents the web page from being embedded in iframe, mitigating clickjacking attacks. X content type options ensures that the browser does not try to guess the MIME type of the content, preventing MIME type sniffing attacks. Set cookie with HTTP only or secure flags secures cookies by making them inaccessible to JavaScript and ensuring they are sent over HTTPS. So security headers helps protect the client and server from a variety of attacks by controlling how the browser behaves with resources and enforcing security policies. Now, there are two ideas that we see here while talking about HTTP headers. One is extensibility. HTTP is highly extensible because headers can be easily added or customized without altering the underlying protocol. Right? We only have to add some kind of metadata and the whole flow of the interaction changes depending on that. Now, headers can be defined and used for various purposes, making HTTP adaptable to new technologies and use cases. For instance, security enhancements, as we just talked about. Headers like strict transport security and for security connections. Custom headers. Developers can create custom headers like X custom header for specific application for their own use cases. Content negotiation, the accept and the accept language and accept encoding headers allows servers to serve different versions of the content depending on the client's preference. So the next part is the idea of remote control. HTTP headers act as kind of a remote control on the server side. They allow the client to send instructions or preferences to the server, influencing how the server responds or processes requests. For example, content type negotiations. Clients can request specific formats using accept header, and the server can respond with the appropriate format. If the client says, I want the HTML format, the server sends the HTML. And if the client says they want JSON, then the server sends the JSON format. Then caching and expiration control. The server can use headers like cache control or expires to control how long a resource should be cached by the client. Then authentication. The client can authenticate itself to the server through authorization header, influencing access control decisions, right? So these provide more capabilities on top of our messages, which are very useful in a lot of instances. Now we have some kind of idea about the headers in HTTP, and we will explore them in more depth when we are going through the demos. Let's move on to the next component of a HTTP message, right? The HTTP method. HTTP methods exist to represent different kinds of actions that a client, like a browser or an API consumer, can request on a server. Instead of every request doing the same thing, methods define the intent. The keyword note here is the intent of the interaction. This gives clear semantic meaning to each type of action, and it is pretty intuitive in that sense. We use get request to fetch some kind of data from the server, and it should not modify anything on the server. We use post to create some data in the server, and post requests have a body, which makes sense because how else would you send the user data to the server? Then we have patch, which is used to update some data. For example, you have a user's profile page where they can update their name, and this also has a request body to send the data to the server. We also have put, which is also used to update data, but what sets it apart from patch is whatever data that comes in request body should completely replace the previous instance. Basically, patch can be thought of as an append action or a selective replacement, while put is a complete replacement. Even though a lot of times developers use put when they should be using patch and go against the semantics. So the thumb rule is always use patch unless you have a specific use case for put. Then we have delete method, and as the name suggests, we use this to delete some kind of resource from the server. And one prevalent idea that we have in the context of HTTP methods is the idea of idempotent and non-idempotent. And what the idea of idempotent means is these HTTP methods can be called multiple times and we can expect the same kind of result. For example, we generally consider the methods get or put or delete in the category of idempotent methods, because just think about it. You're trying to fetch some data from the server, right? It does not matter how many times you fetch it, the data should be same. You should not be able to modify any kind of data in the server. So get is obviously idempotent. And then we have put, because put completely replaces the resource in the server. So it does not matter how many times you replace an old data with the new data, the result will be the same, right? So that is also considered as idempotent. Then we have delete. You can only delete a resource from the server once, because after that it is already deleted. You cannot perform the action multiple times and expect different results, right? The result will always be the same. The resource can only be deleted once. And then we have the idea of non-idempotent. Usually we consider post request to be non-idempotent, because once you submit a request to create some data, let's say a user can create a note using your app, right? They submitted a post request to create a new note, and the first time they submit the request goes through, the response is successful, and a new note is created. And when they do it a second time, we create a new note, right? there are two different results for the same kind of request. So that's why we consider post to be a non-idempotent method, because it produces different results for the same kind of request. After all these HTTP methods, we have one other method which is called the options method. And this has a very interesting use case, which is used in the CORS flow, right? We discussed this before in brief. The CORS flow, which is part of the same origin policy which browsers have. Now, options method, this method you probably won't use directly as a developer, but you will see them once in a while in your browser's network tab in pre-flight requests. So the options method is used to fetch the capabilities of the server for a cross-origin request, also known as CORS, which is used because browsers have same origin policy, which means by default, browsers follow the same origin policy, which restricts web pages from making requests to a domain different from theirs, different from the one serving the web page. And CORS is a security mechanism enforced by browsers to control how web applications interact with resources hosted on different domains, which are cross-origin. And without CORS, browsers block the request made from a web application running on one origin like example.com to a different origin like api.anotherexample.com for security reasons. CORS allows servers to specify who can access their resources and how. In a cross-origin request, there are primarily two types of flows. One is a simple request flow and another one is a pre-flighted request flow. First, let's look at the simple request. Imagine our client, our front end is at the domain example.com and our server is at the domain api.example.com, and we make a GET request which looks something like this. This is how the flow looks like. The client sends a request. The browser automatically adds the origin header to indicate the origin of the request. The request uses a simple method, which are usually get, post, or head, and then it reaches the server. The server checks for the origin header against its CORS policy. If the origin is allowed, the server includes the access control allow origin header in the response and it sends the response. The server responds with the resource and includes the necessary CORS headers. For example, access control allow origin header. And this is what the response looks like. It has the appropriate CORS header which the browser looks for while it parses the response. It sees that our domain, which is the example.com, is different from the host's domain, which is the api.anotherdomain.com. And since these two are different, the browser checks whether the server's response has this header or not, whether it responds with this particular header, access control allow origin. If the server responds with the domain of the client, example.com, or it would also respond with star, which means allow all origins, right? If either of those two conditions are true, then the browser lets the response go through to the client, to whatever the JavaScript client requesting the resource. And imagine if the response looked like this. The client sent the request, the server got the request, and assuming the server did not add the corresponding CORS headers, or assuming the server did not allow this particular domain as the client, then what the server does is it excludes this particular header from the response. So the response looks something like this. And when the browser finally parses it, it sees the absence of this header, and what it does is it blocks this particular response from being parsed. We will get an error in our console, and we will see the error in the network tab as a CORS error. And this is how a simple request flow looks like. Next, we have a pre-flighted request flow for a cross-origin request. And how does a browser distinguish between a simple request flow and a pre-flighted request flow? So these are the three conditions the browser checks before it decides it has to do a pre-flight request, which basically means it has to do a request before the original request to inquire some stuff, to inquire some capabilities, and to let the server know about some capabilities, right? And when does a request qualify as a pre-flighted request? One is the method is not get, post, or head. Example, it is a put request or a delete request. And it is a either or situation, right? Either of these conditions have to be true, then it will be considered as a pre-flighted request. So the first condition is obviously it has to be cross origin request, which means our domain and the server domain has to be different. And the second condition is one of these three. And after that, it will be a CORS request, and inside that, it will be a pre-flighted request. So the first condition is it has to be either a put request or a delete request, or the request includes some non-simple headers. Non-simple headers are basically anything apart from our general headers or request headers. So one example could be an authorization header or some custom headers, right? And the third one is, or the request has a content type other than application form URL encoded or multipart or text plain. These are called general content types or simple content types. So if assuming our application, our client requests the data to be in JSON, in that case, it will be considered as a pre-flighted request. And if you are a front-end engineer or a back-end engineer, you know that mostly we deal with JSON data, right? So most of our requests are considered as a pre-flighted requests. These are the three conditions. Either of them have to be satisfied before we move on, before the browser moves on to make a pre-flight request. So what does a pre-flight request looks like? This is when we finally see the use of options method, right? A pre-flight request is made with an options method, and a pre-flight request looks something like this. It has the method as options. It has the appropriate resource URL and the HTTP version. It has the host header, which is the header of our API, the origin, the domain of the front end, and this header access control request method. So it is basically asking the server whether this method is supported for this URL or not. So it is saying, I am making a cross origin request, and do you support this put method for this route, right? And it also asks whether you support this particular header or not, if it is needed. And the browser sends the options request to the server. The request does not include actual data, right? This does not include any request body or anything. It is just a general inquiry to the server about its capabilities. And after that, if the server is properly handling CORS flow, if the server supports cross-origin requests, it responds something like this. And if the server does not handle CORS requests, then it won't respond with this, and the request will be automatically blocked by our browser. And if it does handle it, it requests with something like this. What it says is, this is the status code of the response, which means there is no content. This is just a general information. We use 204 when there is no content. Then these are the four important headers it responds with. The first one is the access control allow origin. It says, yes, I allow the client's domain, which is example.com, as a cross origin, as a valid cross origin request, right? It can either respond with this, or it can respond with a star, which basically means I allow all types of clients to make requests to me. This is the one valid condition. It is browser checks it. The next is, we asked whether you allow put request for this resource or not. So the server says, yes, I allow these two different kinds of methods. It is the put method and delete method for this resource, for this particular route, right? And the browser checks it off. The next one is, we asked whether you allow authorization header, and the server says, yes, I allow authorization header, and then it is also checked off. And the last one is access control max age. What this means is, the server says, don't make any more pre-flight requests to me, right? It says these configs, whatever I responded with, these will be the same for at least the next 24 hours. So you don't have to keep making more pre-flight requests for every route before you send the original request. So this saves some bandwidth for both our servers and clients. So this is the pre-flight request that the browser makes, and the server responds with the appropriate headers. The browser checks off all these conditions, and then the browser sends the final request, which is the original request that the client wanted to make, and the server responds according to the original request with whatever the operations are required. This is how the typical CORS flow looks like. And now that we understood the theory, let's look at a real demo. Okay, now before we start, let me make this clear that We won't be looking at any code because, as I said, we are learning from first principles, and the rule for that is we try to understand the concepts first, how the underlying mechanism works before we dive into code, before we understand the how. But first we have to understand what. For all these demos that we are going to do in this video and all the other videos in this series, we won't be looking at any code. It does not matter what language the server is written in, what framework it is written in. I'll explain what I am changing in the server, what I have done in the server. For all it matters, it can be implemented in any language. That's that. And this is a tool. It's called Burp Suite, and it is used by ethical hackers, if you may. It has a lot of features, as you can see, but primarily what we are going to use it for is HTTP intercepting or visualizing HTTP traffic, and it offers a quite a nice set of features for that. With that, what I have here is I have a simple front-end app. Again, it could be in any language, and what I want to show is one for our course flow. One is the simple request and one is the pre-flight request, and how they look like in actual browser environment. So let's fire the first simple request. Okay, so we got this response that we are rendering here, and let's inspect the request and response for now, right? If you go here, this is what the request and response looks like, right? We already took a look at all these components, right? The method and the URL and all these headers and the response, the status code and the response headers, the response body. So let's focus on the cores here. What is the first parameter for a request to be considered as a cross origin request by the browser? The first thing is the origin. So this is our localhost 5173 and the host, right? This is our APIs, which is running on the port 3000 of localhost. Since the host and the origin are running on different ports in localhost, by the browser, this is considered as a cross origin request. And according to the same origin policy, we can only make request from localhost 5173 to localhost 5173, right? Since we are not, it is considered as a cross origin request. The headers to focus here is origin header. Let me minimize this. So the headers to focus here is the origin header, which is our origin, the front end's origin, and the host, the domain or the port that you want to connect to, which is the APIs, right? For the request, these are the two important headers. Now let's go to the response now. The thing to focus here is this header, right? As I had explained, the browser makes a cross origin request, and when it gets the response, it checks whether it has the access control allow origin header or not, or whether it has the appropriate port or the domain. So it has the front end's port, right? The 5173, or it could also have star. So in that case, the browser lets the response through. And it does not block it, since according to the core setters, this response is now expected, right? This response is now allowed, and now that's why we are able to get the response, and now we are able to render it in our front end, right? Let's see what happens if we remove this header, right? This access control allow origin header from the server for a simple request. Let me just go and make this change. Okay, I have went ahead and made the change in the server. Now it won't return the appropriate core header, the access control allow origin. Let me refresh this and let's clear this history so that we can focus on the particular request. Now let's fire the same request again. And before we do, let's disable caching so that we can see what a new request looks like, right? So let me fire this. The browser blocked this response, right? It says course error. And why? Let's inspect this request and response. So here, if you see, we have a cross origin request because our origin is 5173 and the host is 3001, and the server does not return an access control allow origin header, right? Because we removed it. And for that reason, the browser has blocked the request because of course error. So this is how the simple request flow looks like. And now let's move on to our pre-flighted request, right? Okay, I have gone ahead and enabled the course again so that we can test the pre-flight request flow. Okay, let me fire this. All right, as you can see here, the first request that went through was the options request, right? The pre-flight request. And then the original request went through. Let's look at them one by one, how the whole flow looked like. Okay, for the pre-flight request, as we have already discussed, the method was options, and it is a cross-origin request because the referrer and the origin are different ports, right? And for that, what the server responded with, it responded with status code 204, no content, because it is just a general inquiry, right? Pre-flight requests are general inquiries. They don't have request bodies or response bodies. And the server responded with access control allow origin with the frontend's domain or port, right? This makes the browser allow the response to go through. That is the first condition. And before that, let's see why a pre-flight request was fired, right? Why this was not considered a simple request. If we investigate the original request, what were the conditions? It is not a simple method, which is get, post, or head, right? That was one of the conditions. So it is already satisfied. But let's look at others. It also has an authorization header that also counts it out of a simple request, right? That is the second one. And the third one is the content type is application JSON, and it is sending a JSON request body, right? All the three conditions are satisfied, but even if one of them was satisfied, it would have still fired a pre-flight request for this. Let's go back to our options pre-flight request analysis. The first one was it allowed the client's domain so that the browser lets the response to go through. The second one, access control allowed methods. So the server says all these methods, get, post, put, delete, these methods are allowed for the server. It lets the client know the capabilities of the server. The third thing is access control allowed headers. It says these are the two headers which are not simple headers that are supported by the server, which is the content type and authorization. Since the client asked for them, if you look at this, access control request method put, the client is asking with the pre-flight request that whether the put method is allowed or not, and whether these two headers, authorization and content type, these two headers are allowed or not. So for that, the server is responding with these headers. It says get, post, put, delete is allowed. It also says content type and authorization is also allowed. We have also set the max age for the access control to 0 for testing purposes, right? Because if we cache this for, let's say, 5 minutes, then pre-flight request won't be fired. That's why this is used for. And the content length is 0 because there is no content. Since the pre-flight request was successful, it returned 204. It is a success status code. The browser let the response go through and it fired the original request, which is the put method. And this is the original request. It has put method, the resource URL, the origin, and the authorization header, the host, the request body, and it responded with a response body, right? And that's how the pre-flight request flow looks like. So the simple request and the pre-flight request flow combined, they make the whole course flow. And this is all you have to understand how course works behind the scenes and why these headers are important and how browsers react to them. Okay, moving on, the next component that I want to cover is response codes. This part, this 200, okay, what are these and why are they needed? HTTP response codes exist to communicate the result of a request in a standardized way. Now you can just look at the response code and see whether the request was successful or not, or what is the state of the server, without looking into the body or without judging from the response message that, okay, so if the request was successful, then I would have expected this structure. If the request was unsuccessful, then I would have expected this structure. If the server crashed, then I would have expected a null object, right? We don't have to make those decisions. We can judge by these status codes. So they quickly inform the client whether the request was successful, resulted in an error, or requires further action. They also help clients handle errors by providing specific codes to identify the problem. For example, unauthorized access will return 401. So now the clients can check whether it is 401 and it can log the user out saying you have to log in again, right? Those kinds of actions, they can be judged with response codes. Or imagine, let's say it was a bad request error because of some invalid value through a form submission. Then the client can ask their user to make changes to their form submission and resubmit, right? Depending on the status code, which was like 400. Also, standardization. HTTP response codes are standardized across all web services, enabling consistency in how servers communicate with different clients, regardless of the platform or language used. It does not matter whether you are making a server in Python or Golang or Rust or JavaScript or Ruby. You have to follow this standard. If the request was successful, you have to return 200. If you created something, you have to return 201. These are the standards and you have to follow them. Now, before HTTP status codes, clients would have to guess the outcome of a request based on the content of the response, as I said, leading to inconsistencies and inefficiencies. HTTP status codes solve this by providing a universal language that all clients and servers understand, streamlining interactions and error handling. On a high level, response codes are 3-digit numbers. They could either start with 1, 2, 3, 4, or 5. And depending on the starting digit, we categorize them as different level of errors or different types of errors. On a high level, the digits starting with 1 are informational responses. 2 are success responses, 3 are redirection, 5 are server errors, 4 are client errors. Response codes starting with 1. This code is sent by the server to indicate that it has received the headers and the client can proceed to send the request body. And when is it used? Commonly used in large uploads. The client sends the headers first. And if the server is okay with the request, it sends 100 continue. So the client can send the rest of the body. Also, there is, which is used for switching protocols, right? We have a use case for that. This indicates that the server is switching protocols as requested by the client, such as upgrading from HTTP to WebSocket. This is not the mostly used response codes that you will encounter on your day-to-day life. So let's focus on these 4, which you will see a lot of times, especially 2, 4, and 5. 200 series, as we know, are used for success responses. And under that, we have 3 mostly used ones. One is 200 and 201 and 204. 200 is the most common code. It indicates that the request was successful and the server is returning the requested resource or performing the requested action. For example, successful GET request where a resource is retrieved. 201, it indicates that the request has been fulfilled and resulted in a creation of a new resource. For example, post request or new form submissions. That's where servers use this response to indicate that a new resource has been created. Then we have 204 that we just saw in a course flow when we send options request, a pre-flight request, and the server responds with 204 saying that there is no content, but these are the information in the form of headers. This also indicates that the request was successful, but there is no content. We also sometimes use it for delete requests, right? The client makes a delete request, you delete the particular resource, but the server says, okay, I've deleted it, but there is no content to return, right? You can just assume that the request was successful. Then we have 300, and in 300, the mostly used ones are 301, 302, and 304. 301 means moved permanently, which means the requested resource has been permanently moved to a new URL. And the future request should use this new URL. For example, let's say initially you had a route called user and eventually you decided to move that route to /person. So in order to maintain backwards compatibility so that old users or old applications that are still using this route don't break, what you do is you add a 301 response for these routes and redirect them to the /person route. So it is a permanent redirect. The next one is 302, which means temporary redirect. The requested resource is temporarily located at a different URL, but the client should continue to use the original URL for future requests. So when do we use this? Let's imagine you are running a campaign or something, and for those couple of hours, you want to redirect a particular route to a new route for catching new traffic or showing a different UI or something like that. But you don't want to stick to that, right? You want to revert the changes. So you want to say to the client that for now I am making a redirect, but later on you should use the original route only. And then we have 304, which says not modified. It indicates that the resource has not been modified since the last time the client requested it. And this we will see soon in a bit when we explore our caching demo. And when do we use it? This is mostly used in conjunction with conditional get requests to allow efficient caching, right? When we are using e-tags to let the client know that the response is not modified, it should use the cached one only instead of downloading the new response. So it just says that it is not modified. So you should keep using your old response, the cached response. Then we have the 400 series errors. And as a backend engineer, I think you will mostly deal with these errors because these are the client errors or errors that are triggered because of some behavior from client. So let's see what are the common ones. The first one is 400. And what this means is it says bad request. And when does it trigger, or when should we fire it? For example, when the client sends invalid data or illogical data or something related to data, right? For example, you are expecting a number and the client sends an array or a string, right? You are expecting an email, but the client sends a phone number, something like that. It's a bad request. That's what it says. And you're letting the client know that there is something wrong with your request format. So fix it and make a new request. The next one is 401, which means unauthorized. When should you fire this? When a request requires authentication, but the client has either failed to provide valid credentials or has not authenticated at all. So let's say you are expecting a JWT token, and either if the JWT token has expired or if the client has not sent the token in the first place. So in those scenarios, you want to say that you are unauthorized. That's when you respond with this status code 401. Next up, we have 403. And it says forbidden, which means the server understood the request, but it refuses to authorize. And this can happen even if the client is authenticated. For example, when a user tries to access a resource, they don't have permission to access. So let's say you are user A and you are trying to delete a resource of user B. So that's when the server says you don't have the necessary permissions to perform this action. So you are forbidden, 403. Next up, we have 404, and it means not found. I think this is the most famous status code, 404. This is fired when the client requests a resource that is unavailable, either because the URL is incorrect or the resource has been deleted. So in those cases, the server says 404, it is not found. Then we have 405, which means method not allowed. When does it get fired? When an invalid HTTP method is used, such as trying to put to a resource that only accepts get or post. This often happens because of typos, right? We are working on frontend, and instead of doing a put request, we do a patch request, or instead of doing a post request, we do a put request. So in those scenarios, server says 405, which means method not allowed. Then we have 409, which means conflict. This has a number of use cases. One of which we can imagine is, let's say in your app, you are allowing users to create folders, right? And the condition is the folder names has to be unique. They cannot create two folders with the same name. When they try to create a new folder, when they submit a post request, you check whether the folder is already existing or not. If it is, you can respond with this error 409 conflict. So the client will understand that a folder with that name already exists and it should try with a new folder name, right? It means conflict. And at last we have 429, which means too many requests. And this is mostly used when we are trying to rate limit the client's request. Rate limit basically means if a client tries to make too many requests in a particular interval, let's say in your server, you have configured it to allow at most 60 requests for a client in 1 second. And if the client tries to exceed that, you can respond with this response code, which says 429, too many requests. Okay, let's move on to the 500 series. And we have the most famous one, which is the 500, which means internal server error. This is often used for unexpected conditions in server. Some process broke or some exceptions were raised which were not handled in the server. So something unexpected happened at the server. So instead of just returning a empty response or just breaking or hanging the request, we respond with 500 internal server errors. The client knows that something went wrong with the server. Then we have 501, which means not implemented. For example, when the server does not support the requested HTTP method or functionality, but it plans to add it soon. So that's when we add a 501, which means currently it is not supported. It might be in the future, right? So we are trying to get that intention through to the client, so that it is not implemented yet. Then we have 502, right? It means bad gateway. We usually see this in proxies like Nginx. It means when a server acts as a proxy, like in a load balance system or reverse proxy, and the upstream server returns an invalid response. So that's when 502 is returned. This is not something we return intentionally. This is handled mostly by proxies and load balancers. Then we have 503s, which means service unavailable. When the service is down, when the service is temporarily unable to handle the request, such as during high traffic or when it is going maintenance. So that's when you return 503 to let the client know that the service is unavailable right now and it should try again later. At last, we have 504, which means gateway timeout. It is similar to 502, but this specifically means that the upstream server failed to respond within timeout period. Let's say you're using Nginx and Nginx could not get a response from our original server, which is running behind it. So that's when Nginx responds with 504 gateway timeout, that it did not receive any response from our original server. That's why it says timeout. Okay, that's all. That's pretty much all the response codes you need to know to work with 95% of use cases. Now, in order to solidify our understanding, let's look at a quick demo where we look at some of these responses. Okay, now again, we have a front-end app for this demo where we are trying to emulate some of the response codes, and there is a server running which will respond with different status codes, right? Okay, so what we'll do is let's just fire all of these requests, then we will examine what the responses look like. Let me go ahead and 200. Okay, created this one. All right, we have fired all these requests. Let's go through one by one. So as you can see, we have all these options requests before each original request, because these are cross origin requests. The browser need to do pre-flight requests to support those. Let's go through all the original requests one by one to see what are the responses looks like. Okay, the first one was 200. Okay, as I said, this is a successful response, which means request was successful, right? The status code is 200. And the next one is a post request, which says 201, which means created, and the server response, even though it is a mock request and a mock response, this is what usually it looks like. The resource was created successfully and the status code is 201. Then we have 401 bad request. It says bad request, missing required data. Then we have 401, which means unauthorized, which typically means either you have not included the token, the JWT token or the cookie or whatever authentication mechanism you're using, whether you have not included that, or even if you have, it has expired or it is not valid anymore. Next, we have forbidden, which means you are trying to perform some action which you're not authorized to do, right? That's why it says 403 forbidden. You do not have access. Next up, we have 404, which means not found. And the server says something like not found, the requested resource could not be found. Next, we have 409 conflict, which is resource already exists. So this could happen when, as our previous example, maybe you already have a folder and you're trying to create a folder with the same name again. So that's why the server says resource already exists, right? Then we have internal server error, which is 500, and the server just says internal server error without letting the client know too much of the information for security reasons. Then we have 503 service unavailable, please try again later, right? That's pretty much covers most of the status codes that we have discussed and that we saw in this demo. Okay, moving on, let's explore another interesting concept, HTTP caching. What does HTTP caching mean? HTTP caching is a technique to store copies of responses for reuse, reducing the need to repeated requests to the server. This improves load time, reduces bandwidth, and decreases server load, right? Because the client does not need to download a lot of data and the server does not need to send a lot of data. If the data is not changed, this client can just reuse the old data, right? That's what caching means, reusing the old data if the data is not changed. In order to understand this, let's just go through a demo instead of going it theoretically, how it looks like practically in a browser environment. Okay, let's go through the request cycle and understand how caching works by following the trail. Let me just do a refresh. So when we first render the page, we are doing a fetch operation. So let's start from there. Okay, we fired all these requests and what you want is the last one, right? Because these are just JavaScript files and CSS and stuff. Okay, what happened in the last request? Let's see. We did a GET request to this endpoint API resource, and there is nothing else in the request headers that we should focus on right now, right? Let's come to the response. What did the server respond with? The first important thing is this one, cache control. What it says is you should maintain the cache for this resource for maximum 10 seconds, right? This is the first important header. The next is e-tag. E-tag is basically a hash. So for the sake of this example, we are using a random number, but e-tags are usually hashes which are computed from a response. For example, the server might have taken this response, hashed it, and sent us that hash in the form of e-tag, right? And we will see what is the use of that in the next request. The next important header is last modified. With this, what the server is trying to say is this is the last time this request was modified. And judging from this time and date, we can decide whether we should use the old resource, the cached resource, or request for a new one. These are the three important headers that we are going to use for caching. Okay. So that was the initial request. And in this request, the server responded with a 200 along with the requested resource, whatever that is. We won't focus on that. We are just seeing there is a response body. All right. What happens when we do a fetch operation for the same resource, right? Let's do a fetch. Okay. What happened here? Let's look at the response. Let's focus on the request first. We are again doing a GET request to this endpoint. And now the headers to focus in the request is these two headers. If none match and if modified since. What we are trying to say to the server is if the e tag, the hashed version of the response object, the e tag of the requested resource is not the same as this one, which we have with us in the browser, or if the request has been modified after this, which means we have the outdated version, right? We are saying if the e tag does not match or if the request has been modified after this, then send us a new resource, then send us the updated resource. Otherwise, I will just use my cached version, which I have with me in the browser cache. And to that, what server says is it responds with 304 not modified. And we just talked about different response codes, right? And 304 meant the requested resource has not been modified ever since. What the server did was it checked the if none match header, which is the E tag, and it also checked the last modified. And since the resource matched either the E tag or the last modified, it sent the client a 304 response, which means the requested resource has not been modified ever since from the last time you fetched it. So you can go ahead and use your cached version. Let's update the resource. For now, let's clear this and let's fire an update resource. Okay, what happened here? Let's explore the first request. Okay, ideally we should have done a patch request or put request, but for the sake of this example again, we just fired a request, a post request. Okay, we updated the resource and the server responded with 200 okay, and it also sent us a new E tag, right, 2943. And after that, the client did a new get request. In this, as you can see, the client sent the old E tag, which was 3141, our cached version. So client did a get request with the old E tag and the last modified since to the server, and the server responded with 200 instead of 304 because the resource has been modified after that, right? Because we did a update resource request and the server responded with 2943, which is the updated E tag, the last modified, etc. And let's go ahead again, do a fetch request. Okay, and what do we have here? We are again using the E tag that was just provided by the server in this request, right? This was 200 and the server provided us with a new E tag. We are using that E tag and the last modified value, and we are doing another get request. So the server checked it again, and since it is the latest version of the resource, it again responded with 304 not modified. So this is how you handle caching using the HTTP protocol, using different headers in server and client. Even though in a production setting, it gets a lot complicated because the server has to manually implement and manage all these E tags. And if by mistake forgot to update an E tag, right, then the client will continue to use the cached version with the outdated resource, which is not a good idea. Nowadays, we have better solutions for caching, right? For example, React Query, which is a complete client-side caching. So the client has the complete power over when it wants to use a cached resource and when it wants to refetch, right? At what interval, and all these powerful capabilities, which is, in my opinion, a much better solution compared to the traditional HTTP based caching. But it is good to know that we have this option. If our use case is simple enough, then we can go ahead and use HTTP based caching. Moving on, another important topic that usually comes up in client server model in HTTP is content negotiation. We already looked at some of these headers, for example, accept, the content type, application JSON, etc. So this is an important topic to understand how clients and servers exchange information about different types and encoding and representation of the content. This is basically a mechanism using which client and server agree on the best format to exchange data. The client can indicate its preferred format like JSON or XML or HTML, and the server will try to respond with a compatible format, or if not available, a fallback format. That is the whole idea. To look at a high level, we have generally three types of content negotiation. One is a media type, which means the client specifies the desired format through the accept header, which is application JSON or XML. Then we have the language negotiation. The client requests content in a specific language using the accept language header. It could be English or Spanish. Then we have encoding negotiation, right? The client specifies which encoding it supports using the accept encoding header like gzip or deflate. and the server responds with that compression format. We have a topic which is HTTP compression, which is also part of this topic only. So we will quickly see that also in the demo. That's the whole idea. And let's just jump into the demo to understand how it works. And again, there is a server running, which will help us understand different types of content negotiation. And this is a front-end client through which we will communicate with our server. So let's just try out different types of requests, and we'll see how the headers differ and how the responses differ depending on the types of headers the client is sending. Okay, let's first just try the default one, which is a language is English, the format is JSON, and the preferred encoding is gzip. So let's do a fetch resource, and this is what the request and response looks like. Okay, so it was a GET request to this endpoint. And what we said is the language we are saying is English. We are sending that information using the accept language header, that we prefer the English language. Then what we are saying is the format is JSON, right? We send that with accept application JSON, and there is the encoding header, right? That we are saying accept encoding. The browser supports these kinds of encodings, right? gzip, deflate, vr, and zstd. So we said we are expecting English and in JSON format. So this is how the server responds with it. It is sending us a JSON and it is in English. So let's try one thing. Let's make it to Spanish and see how the response differs. I made it Spanish and I did another fetch. Okay, so let's see how this differs. In this, the only thing that changed was instead of accept language English, in the header, the client said accepted language is Spanish. So depending on that, the server was able to update the response. So instead of sending it in English, since the client prefers Spanish, the server responded with Spanish. And what if we change the format from JSON to XML and we do a fetch? And we look at this, what changed here? We are saying our accepted format is XML and the accepted language is Spanish. This is the XML format and the language is Spanish. And on a high level, these are the benefits of using content negotiation based headers, right? The client can let the server know what are its preferences, whether it is the data format or the language of the data. And depending on that, the server can decide to send according to that format. It can make the life of the client easier by sticking to the preferences. Those are the primarily two type of content negotiations. While we are discussing content negotiation, there is one interesting topic which falls under the same umbrella, which is HTTP based compression. It could be either gzip, deflate, or other formats, right? So let's look at why do we need compression and how does it work. So now what I've done is I've gone ahead and replaced the JSON response with a very large file of 11,000 entries. Now let's fire the request. Okay, this is the response and the size is 3.8 MB since it's a very large file. And let's look how the response looks like. This is what it looks like because we are compressing the file on the server side with gzip encoding, right? Here it says content encoding is gzip because the client says it accepts encoding of gzip, one of the encoding formats. Now, why do we use it? To show that, let me just go and disable compression in the server side. Okay. And now that I have disabled the compression, let's fire the same request again. And as you can see, the significant increase in the size. It's the same file, right? It's the same file with 11,000 entries. And because we are using compression, the file size was 3.8 MB. And now that we have disabled it, the file size becomes 26 MB. That's a huge increase in size. And imagine every client having to download that file. It causes a lot of waste of bandwidth. And that is why we need compression, so that if the response size is very large, we can compress it to a format, and on the client side, the browser can decompress it and it will get the same response. And this is another important topic which we won't really work with, it's good to know that it exists behind the scenes. In the early days of HTTP, specifically HTTP 1.0, each request response cycle required a separate connection to the server. Now, this created inefficiencies since establishing and closing TCP connections is resource intensive and slow. To address this, persistent connections were introduced in HTTP 1.1. Now, with persistent connections, a single TCP connection can be reused for multiple requests and responses, avoiding the overhead of opening and closing a collection for every interaction. And for achieving that, they introduced this header called keep alive. A keep alive is the mechanism that enables persistent connections. It allows the client and server to reuse the same connection for multiple request responses until one of them decides to close it. So what are some key points to remember here? In HTTP 1.1, connections are persistent by default. We won't have to do anything explicitly about them, meaning they remain open for further requests unless explicitly closed. And multiple HTTP requests and responses can be sent over a single connection. This reduces latency and saves resources as fewer connections need to be established. Now, the second thing is the keep alive header. While persistent connections are default in HTTP 1.1, the connection keep alive header is still sometimes used to explicitly ask the server to keep the connection open. This header can also include options like how long the connection should remain open with a timeout, or how many requests can be sent before the connection is closed with the max value. Now, the third thing is when connection is set to close, and when that is specified, the connection is closed after the response is sent. This was the behavior in HTTP 1.0 by default, and it can still be explicitly enforced in HTTP 1.1. So that is some amount of information you just have to understand, but you usually won't be working with them. The default values work fine. One last topic that I want to cover is handling large requests and responses. How server takes in large requests like files, video files, image files, audio files, any kind of file which are very large compared to our typical JSON, and how client can receive large responses in the same way. So let's just jump into the demo and see how it usually works. Now here we have two examples. In one, we will see how clients can send large requests to the server. And in the second one, we'll see how servers can send large responses to the client. First one is multipart request. Multipart is usually used for sending large files or any kind of files to the server from the client. And the difference between our typical JSON request body is in multipart requests, the file, the data of the file, the binary data is transferred to the server in parts, in different parts. That's why it is called multipart request. So let's see how it looks like. I have selected a picture and let's click on upload file. Now let's look at the response of this. Here is what the request looks like. It is a post request and we are specifying a content length, and our content type is multipart form data. And this is the important part, the boundary. And why we need this is, since our binary data, the binary data of the file is transferred in parts, we want to specify what is going to be the delimiter, what will separate the parts, right? We need some kind of code that will separate the parts. So we are saying this will be our delimiter. And if we do a search here, we have the delimiter at the start of the binary data, and the next occurrence is at the end of it, when all the binary data ends in the request body, right? That is the use of the boundary parameter, and that is how we transfer a large file to the server, and the server can read the file, responds with some details of the file in order to say that the upload was successful. The idea is whenever we want to transfer large files to the server, we should use multipart requests. Okay. Now the second thing is receiving large responses from the server. For this demo, I have used a large text file in the server side, and we want to stream the data to the client side in chunks. That's what we want to do. So let's start the So let's start the request and see how it looks like. We click on stream data. So as you can see, this is the first chunk. Okay, so if you go here, you can see that we are receiving chunks continuously from the server in different requests. So the request is pretty much a normal request. It is a GET request. Let's look at the response, what the response looks like. These are the three important things that we have to consider. One is content type. It is saying that it is not a text content, right? It is a text event stream, which says it will stream the data to the client through different events. And the second one is the connection keep alive. It says keep the connection alive until all the data is sent. And if you see here, we are still receiving the chunks, and we can keep scrolling and until the file is completely transferred, the server will keep sending the data in chunks. And how does it work? Because of these headers, the content type text event stream and the connection keep live, right? And the client keeps appending all the data that it is receiving from the server and constructing this whole text file. And that is how we transfer a large file from a server to the client using chunk transfer or text event stream. And the last thing before we end this lesson, I just want to give a brief idea about what these terms mean, SSL or TLS or HTTPS. Even though we don't explicitly work with them, it's good to know what are these. SSL was the original protocol for securing communications between client, like a web browser, and a server. It encrypts data so that sensitive information like passwords or credit card numbers cannot be intercepted by attackers, right? It was the original encryption mechanism between clients and server. Now, currently SSL is outdated due to some security vulnerabilities and has been replaced by TLS. So this is the modern version of the encryption that client and servers use for data transmission. TLS is a modern and more secure version of SSL. It encrypts data in transit, ensuring that any data sent between the client and server is protected from interception and tampering. How it works is TLS uses certificates to authenticate the server and establish an encrypted connection, preventing eavesdropping and data breaches. TLS is continuously updated with newer versions offering better security. The current recommended version is TLS 1. And what is HTTPS then? HTTPS is basically HTTP, but more security features, which are provided by SSL or TLS. Initially, it was SSL and now it is TLS. The underlying mechanism is TLS, and HTTPS is the one which uses TLS. How it works is when you visit a website using HTTPS, TLS encrypts the communication between your browser and the server. This protects sensitive data like login credentials from being intercepted by the attackers. And that much information is more than enough on this topic. That's all you need to know about TLS and HTTPS to work on application level. Great. We talked about a lot of stuff. I hope you're able to digest that. And I hope you rewatch some of the sections so that you're able to internalize all of them. And overall, this is all you need to know about HTTP. At least, of course, there are more stuff to read if you want on HTTP or TLS or TCP protocol, different components of HTTP. But in order to work on backend systems, if you understand this much, if you internalize this much, and you can visualize the whole flow of all the components that we talked about today, then you're good to go. You'll be able to understand all you need to understand, and you'll be able to debug most of the stuff now that you understand how the system works behind the scenes and what are the components that come into play in different flows. That's all about HTTP.